So, I have gotten via email a request to do a problem like one on the exam. The exam is due on Monday, so we'll have time to answer questions during Monday's problem session thing. But if you have any and you want to think about them while we're setting this one up, we can also talk about it today. So the question that I had was, let me check something real quick. Question that I had was from somebody who doesn't appear to be here yet. But we can go ahead and get started, and hopefully they'll get here soon, or they can watch the VOD later. So it was to do one like number 11. So number 11 was a word problem that went a little bit like this. Alright, so we have our setup sentence that the hypotenuse that the problem has named z of a right triangle is increasing at a rate of 3 inches per second, while the base of that same right triangle remains constant, and we've named that one x, and it stays constant at 12. And then the actual question So our actual question is if theta is the non-right angle opposite x. I'll let you just read the rest. So, okay. Whenever you have a word problem, the first thing you want to answer is, what type of problem is this? How are we going to approach this? So with this setup, what type of problem are we looking at? So some of the key things to look at are that right there, right? So the information that we're giving tells us something about a rate of change of something. And the question is asking about the rate of change of something else. Right? So anytime we have a setup like that, we're looking at a related rates problem, or at least we probably are. Yeah, exactly. There we go. So we've got a related rates problem. We know one rate. We know the rate of z. And we want to know the rate of theta. And what else do we know stuff about? We'll revisit that in a second, but one thing we do know just from here, in addition to these numbers, is that z is actually a function of t. Right? We don't necessarily have to write it down that way each time, but we need to remember that z is actually a function of t, and so is theta. Right? Both of these are going to be changing with respect to time. So, one of the first things that we should do with many word problems, but especially related rates problems, is draw a picture. This is talking about a right triangle. So we've got this guy. The problem names the hypotenuse z, so we might as well put it there. And it names the base x, so we can put this there. Now we just have to figure out what theta is. I think that's the last variable that we have here. And so it says theta is the non-right angle, so it's definitely not this one. Right. Maybe not put an X there. Let's say we're not going to be using this angle. Right? And the other clue that it gives us is it's the angle opposite X. Right? So that means it's going to be this guy. Right? This one here is the one adjacent to X. Right? It's the one that's touching it. But this problem is telling us that we're looking at the angle opposite X. Right? So, can we think of any ways we have to relate a side X, the hypotenuse, and the angle opposite X? there was. So that old mnemonic of SOHCAHTOA tells us that if we want to relate an angle with something it's opposite to and the hypotenuse, then we use sine. Right? The ka means that if we wanted to relate something adjacent and the hypotenuse, then we'd use cosine. And if we want to use something opposite and adjacent, we'd use tangent. Right? But we have something where we want to look at the opposite side and the hypotenuse, so we're looking at sine. So now we have the two things that we know one rate and we want to find the other in one relationship, right? Because remember, an equation is a relationship, at least as far as the related part of related rates matters. Right? So what do we need to do now? We actually have a couple options here. So one thing we want to do is we have this equation that relates the variables. We want to relate their rates, right? Which means we need to get the derivative out of it. And specifically, we want to find the derivative of theta with respect to t. So the thing that I would recommend doing first, like I said, there's a couple different ways for it. But the thing that I would recommend doing first is isolating theta, right? So that we can just take the derivative of theta and figure out what the other side is going to be. All right. Let's give us a little bit extra room. And we isolate theta in this equation by taking sine inverse of both sides. Right. Now, if we want the derivative of theta with respect to t, which we do, that's what the problem was asking for, that's going to be the derivative with respect to t of the other side as well. So I'm going to leave this here. But at the moment, we have a little bit excessive variables, right? We know what dz dt is, and we know what d theta d, or we want to find what d theta dt is. We don't really know anything about the rate of x, so what can we do about that? Looking back at the word problem. Yeah, we know that x equals 12. Right? It's not a function of t. It's just 12 no matter what. Right? So we want to find the derivative on the left, which means we have to find the derivative on the right. So what rule do we need to use to find that derivative? Is this one we just know? Do we need to use a special rule for it? What are we going to do about this derivative? So the chain rule is the rule we're going to need for this guy, right? We don't have anything that tells us about sine inverse of a constant over a variable in particular, right? So we're going to need to, use the chain rule on this guy. So what's the outside function going to be? What is the thing that something's being plugged into, and what's the thing that's being plugged in? Yeah. Though for this particular instance, I'm going to use t, because that's the variable we're taking the derivative with respect to. All right, so the outside is sine inverse of t. So what's being plugged in? So to get sine inverse of 12 over z, what are we plugging into sine inverse of t? Yeah, 12 over z. And I'm going to rewrite it just a little bit to make our next step easier. So what's the derivative of sine inverse of t? And I'm not actually going to wait too long for this one, because this is one that we really just need to remember, right? Well, remember or write it down or have it at hand. It's basically one from a table that should just be something we have at hand. Right? And so the derivative of sine inverse is 1 over the square root of 1 minus t squared. And what about 12 times z to the negative 1? What rule do we need to use there? Yeah, so that's using the power rule, right? Though we need to be a little bit careful here, because this requires the use of the generalized power rule, right? We're not, if this was 12 times t to the negative 1, then we just use the power rule like you have there, like we have written here. But this is 12 times a function of t to the negative 1, right? So all of that works out the same, and then we pick up, a derivative of the function in question. Right, so that's using our generalized power rule. Which I know that's probably too small to be read easily here, but for folks who are watching this later without my commentary. Just wanted to throw that on there. Right, so continuing down, that means that we take the derivative of the outside with the inside plugged in. Then we multiply it by the derivative of the inside. Alright, so now we need to plug some of the stuff in. So what we have here we have to plug in for. So we have our d theta dt, but inside of it we have both z and dz dt. Right? And we want to just have a number for d theta dt. That would be ideal. Right? So we know that dz dt equals 3. Right? So if we go over here, we've got that we can plug 3 in for there. And what about z? Do we have anything that tells us what z should be? Maybe this bit right here, where the problem directly tells us what it wants z to be. So usually if when you take the derivative there's some variable left over, it should be part of the text of the problem. Right, so whether it says it in more words, like the difference between dz dt and a rate of 3 inches per second, or it just flat out says, yeah, we want z to be 25, Right? The problem should tell you what all those variables are. Right? So either you need to check over your derivative work and make sure that there's not some variable there that shouldn't be there, or take a good long look at the word of the word problem. And so we probably wouldn't want to leave this like this. But because we can simplify some things here, right? This is 1 over the square root of right, just simplifying those powers and multiplying some stuff together. Right, if we let that 1 be 625 divided by 625, we get that this is 1 over the square root of 481 divided by 625. Right, we've talked before about if we have a single term in the denominator, then we can simplify the fraction by flipping that over. So this becomes square root of 625 over 481. And we got 625 by squaring 25 in the first place, so we know what that square root is, at least on top. We don't know what square root of 481 is. And we know that 625 is 25 times 25. So we get that theta itself is actually decreasing, which is what we might expect, that angle is getting sharper and pointier. And it's decreasing by whatever this number is. No, it's not decreasing very fast. That's a pretty big denominator compared to that numerator. So, do we have any questions? Probably none that we can read from this distance away, but do we have any questions about anything we did here? Also, do we have any questions about the exam? Either one of those can be thrown into chat at the moment. All right. Yeah, we can do a logarithmic differentiation problem. I'm going to give it another second to see if there are any here or anybody else has something to throw up. And then we'll do a logarithmic differentiation. I'll leave it at that. So, this problem specifically tells you what type of problem it is, so we're going to use logarithmic differentiation. So what's the first step of logarithmic differentiation? So the hint there is in the first word of the type of problem it is. The first thing you do with a logarithmic differentiation problem is you take the log of the function. Right. I'm gonna cheat. Ha. Okay, so if we're taking the log of this guy, which log rule are we going to want to use first to start to simplify this guy? Remember, we've got, for logarithms, we basically have the quotient rule, the product rule, and the power rule. So which one of those needs to happen first for this guy? The power rule, right? And that's because there's one power that's over everything, right? The fact that this power is affecting everything else in the log means that we've got to do something with that first, right? And remember that the power rule for logarithms turns powers into multiplication, right? So we take that power and we multiply it by the log of the rest of this stuff. And since you're generally not going to do the power rule twice in a row, that means that the product and quotient rule are next. And remember, we talked about in class, we can kind of do this all at the same time, right? We just need to identify all of the factors. I'm trying to get colors that'll show up here. Right, so finding all of the factors of the numerator and the denominator, giving each of them their own logarithm, and making it subtraction if it was in the denominator and addition if it was in the numerator. So since this 22 was in front of the log of the whole thing, that means the 22 needs to be in front of each of these pieces. Right? So we can either write 22 in front of each of those pieces, or put everything we have here in parentheses, brackets. Well, almost got there. And I've been doing it a little bad here. This really shouldn't be common log. It should be ln. Right, that doesn't change anything we've done. It just makes our final answer a lot nicer. And, you know, meant I might have been able to fit it all into one line if I'd been doing it properly all along. All right. So, is this as simplified as we want it to be? So that would be our next step, right? If we stopped here, if we stopped simplifying at this point, then what we're going to be doing is for each of those logs, right, we take the derivative of the inside, put it on top, and put the inside on the bottom. Right? So are those insides as simplified as we want them to be? What would we need to do in order to take the derivative of the insides? For really all of these. So for all three of these insides, right, if we were to stop here and just go ahead and take the derivative, then we would have to use the generalized power rule to take the derivative of that inside. Right, which is honestly not that bad, right? It's not a big thing. But the whole point of doing logarithmic differentiation is to not have to use the generalized power rule, right? And instead use the logarithmic power rule. Oops. Right, so for this first one, we're going to pull out this power. For the second one, we're going to pull out this power. And for the third one, we're going to pull out this power. Right, and that's about as simplified as we can make it, right? We could technically do something with this guy. We could do the product rule again, but that doesn't actually simplify really anything for us. But the other guys all have sums in them, right? Or differences. And we don't have a rule that tells us what to do with logarithms that have sum or differences on the inside. Right? We only have log rules for powers, products, and quotients. Right? So we have fully simplified, fully expanded this logarithmic equation. So the rule that you were talking about before, right, the one that we have over here, says that if we take the derivative of what we have here, then that will be the derivative that we want divided by the function itself. So if we take the derivative of what we have here, multiply it by the function itself, then we'll get the derivative we want, right? So f prime of x divided by f of x is going to equal the derivative with respect to x of, oh boy, I'm going to write it again. It's really the only problem I have with logarithmic differentiation is you end up writing the same thing a whole lot. That should be this and then this. Okay. Alrighty, so I'll go ahead and do the whole part, the hard part, which is pulling this 22 out. Then what do we get as the derivative of this first term? So this rule that we have over here doesn't just magically apply for the f that the problem is talking about, it applies for every function. So what's the derivative of 2x minus 1? Let's try that one. Two, right? And then we put the inside function here. So what's the derivative of 9x squared plus 2? All right, 18x. And then we take the inside and just pop it down here. So what's the derivative of the last logarithmic term we have there? So what's the derivative of the whole thing? That's the derivative of 3x, but what's the derivative of the whole thing? Yeah. Alright, so we take that derivative of 3x, and then just put 3x on the bottom. Alright, so we've got some things that can cancel out, that 3 and that 3x, this 4 and the 2, so we get as our final answer for the derivative of the log of the function we care about. Right? Which our rules for logarithmic differentiation tell us is equal to this. Now, we don't actually want to find f prime of x divided by f of x. We just want to find f prime of x. So, let me get us back over here. So, f prime of x is going to equal this times oops, that's not going to work until I do that. Whoa, that's not what I wanted it to do. Times this. Man, logarithmic differentiation problems are a lot better when you can just copy and paste. Alright, so this is the derivative of ln of f of x. And this is f of x. And when we multiply those things together, we get the derivative of f of x. Yeah. Let's see, is that far enough up, or do I need to do some more? Aight. Any questions about any of the steps we got here? Or any other questions about exam stuff in general? We'd have to be pretty quick about it. We might not be able to work through a whole thing, but we can talk about some of the problems for a little bit. Any other questions about stuff in general? Well, this is about 10 minutes early, but I think we'd probably have time for me maybe to write most of the summary of the section on the board, and then we'd have to go. So it doesn't seem very useful to do that and then wait a whole weekend and then say, hey, you remember what I wrote up there before? If there are no further questions, we'll probably just go ahead and call it here. We'll just do 4.3 on Monday, so there'll be no new reading summary up, so you can have more time to focus on the exam and not have to worry about reading a new section. So it works out. remember the exam is due Monday, like, I think, yeah, the minute before midnight on Monday, so you have all day Monday. You need to submit something on Canvas, a picture, a scan, something like that. Something that I can read, and it would be super great and handy if it was actually, like, facing up, as opposed to some sort of weird orientation. Yeah, I don't know any other announcements. I'm kind of stalling. Yeah, yep. We're going to be doing this for the rest of the semester. This time, this channel, at our usual class times, for the next couple weeks. Mm-hmm. Yeah. Yeah, so it's another opportunity to ask questions since the exam isn't due until the end of the day. Then you can have that time to ask more questions if you have some. Probably not about these two problems, unless you have specific questions about what we did here. But if there are other problems that we have questions about, then yeah. Any other questions about stuff? Alrighty, well, I will see folks on Monday at the same time, same place. And I hope y'all have a good weekend.